Hi there, welcome back. This is Dr. Matthew J. Traum again. This is the third video in our lecture on the hydraulic jump and Reynolds transport theorem. We ended on this slide, which essentially showed the Cedarburg River going from supercritical flow to subcritical flow, and the demarcation line between those two fluid regimes is a linear hydraulic jump. Now, I did want to show you a movie of this river actually flowing, and the thing that you want to look for is that the location of this hydraulic jump is essentially fixed in space, and that's because the volume flow rate over the spillway is essentially fixed, and so the hydraulic jump doesn't move upstream or downstream as a function of time. And it turns out that we will see the same thing with the radial hydraulic jump. Once we fix a volume flow rate, the radial hydraulic jump will assume a particular radius that won't change very much. So let me show you that video. Okay, so here's the river flowing, and you can see the hydraulic jump is essentially fixed in location, doesn't change. Play it one more time. Fixed in location, doesn't change as the fluid is flowing, because again the volume flow rate over the spillway is essentially constant. Okay, so let's move on to the next slide. So here, now that we have an equation for the Froude number, it's instructive to compare that equation to other similar equations, with the realization that hydraulic jumps are to surface waves essentially what sonic booms are to external flows around, for example, transonic aircraft. And so what I have here is an image of a jet fighter aircraft that's passing from subsonic to supersonic velocity, and in so doing it's creating this sonic boom, which is essentially a shock wave that's that particular shape, because this is a bow shock produced by the leading edge of the aircraft as the aircraft is pushing through it, and it's a dramatic change in the thermodynamic properties of the fluid, which essentially causes this mass condensation of water vapor that makes it look like a cloud. So if you look at the two equations, this one is the equation for the Froude number, which again is the ratio of the flow velocity to the surface wave propagation velocity in open channel flow, and this equation is the equation for Mach number, which again is a ratio of the fluid velocity to the speed of sound in a three-dimensional fluid field. So you can see that the equations are essentially identical, and just like as Froude number goes from less than 1 to greater than 1, you go from subcritical to supercritical flow through a hydraulic jump, as the Mach number goes from subsonic to supersonic, that is less than 1 to greater than 1. As you achieve a Mach number of 1, you essentially get a shock wave, a sonic boom, which is the result of transitioning from one fluid regime to another fluid regime, where information can no longer propagate upstream to let the upstream fluid know that a jet aircraft, for example, is coming. So that's the similarity, the analogy between those two fluid mechanical phenomena. Pretty interesting. Okay, so we're now going to move from linear hydraulic jumps into circular hydraulic jumps, and these are also called radial hydraulic jumps. And I'm going to just kind of explain some of the geometry here and give you a sense of the important parameters, which will eventually lead us to understand why the hydraulic jump interrogator is designed with the variables that can be changed that it has. So here is just a picture of a sink, and you have probably produced a number of hydraulic jumps probably every day of your life. You produced hydraulic jumps without even realizing it or knowing what to look for, because every time you turn on water in a sink, you essentially create a radial hydraulic jump. So the fluid comes down and then it spreads out radially, and it is very fast and very thin for some region, and then all of a sudden it changes from supercritical to subcritical flow and undergoes this very dramatic jump, which you can see here in this in this image, and then the fluid is of a different structure downstream of the jump. So another way of looking at it is through this schematic. So we have a particular fixed volume flow rate, which is represented by Q with a dot on the top, so Q dot. That volume flow rate flows down, strikes some sort of solid target, and then the liquid spreads outwards with some radial velocity, which is actually a function of the radial distance from the location of the fluid striking at the target. Now we still have the equation which is still true for radiohydraulic jumps for the Froude number, which is the velocity of the fluid divided by the speed of information propagation or surface wave propagation in the fluid. And then we have the second equation, which essentially comes from mass conservation, which tells us that the volume flow rate, which is fixed, is equal to a local radial velocity multiplied by 2 pi RH, where R is the radial location and H is the height of the fluid before the hydraulic jump. Now, what's important here is that Q dot, as I said before, is fixed. That's a fixed volume flow rate. And as R is increased, as you move farther and farther away from the point where the fluid struck the surface, the value of R goes up and the value of H remains essentially unchanged. So if Q is fixed, if H is unchanged and R is going up, what that means is that V has to decrease. And as V decreases, this V as a function of R is the flow velocity. So as V decreases, the velocity of the flow decreases, the rate of surface propagation, surface information propagation is fixed, and so the Froude number is constantly dropping as you get farther and farther away from the center of the hydraulic jump. And as the Froude number drops, it eventually reaches a value of 1, which is again that transition from supercritical to subcritical flow, which creates this hydraulic jump. So in a very kind of rudimentary but still quantitative way, that is an even further explanation of what creates a hydraulic jump. It's essentially the reduction of the velocity as a result of mass conservation as the velocity, or as the fluid moves outwards from this point of contact in the stream that's essentially hitting your kitchen sink. Okay, so I've reached my 7 minutes for this video, so I'll pause here and we'll come back for the next video and pick up the lecture in a few minutes after you guys take a break. Okay, see you in a few moments.